All right, let's get back into it. So what we're getting into here, and we're going to go a little bit past time because it's kind of important that we hit the mark here so that we have a good understanding of what's going to go on this afternoon. But what we're going to be looking at are electrochemical cells. And so this is kind of the application that's going to tie together redox reactions and the concept of spontaneity from thermodynamics. And now when it comes to electrochemical cells, there's a lot of different names for an electrochemical cell. You can hear it referred to as a galvanic cell. You can hear it referred to as a voltaic cell. We kind of tend to think of these mostly, these are batteries. This is basically what a battery is. Now, the kinds of batteries that we're going to make today are far different from commercial batteries. Commercial batteries use mainly pastes or some other kind of mesh system to make everything very compacted. We're going to spread things out a little bit more. We've got the room to do so, and we're not trying to sell some sort of commercial product that needs to fit in a particular space. So that's going to be kind of our advantage and our curse at the same time with these batteries that we're going to make this afternoon. Now, when it comes to these batteries, these electrochemical cells, what we're talking about here is the conversion of chemical energy, the process involved in this redox reaction, to actually doing electrical work and being able to move a current over a space. And so there are a couple of things that are there that have to be there in order for all of this to work. First of all, we need a place for this oxidation reaction to occur. We call that place the anode. So the anode is the part of the cell where we see this oxidation taking place. And the cathode is the part of the cell where we see the reduction taking place. Now, I really don't have a great mnemonic for keeping cathode and anode straight. The only way that we can kind of put it together that makes a little bit of sense is that anode and oxidation both start with vowels, and cathode and reduction both start with consonants. It's not great, but it's something. And what we will see is that in every electrochemical cell, electrons will travel from the cathode from the anode into the cathode. Oh, it is my fault. So we're going to see electrons always flowing from that anode into the cathode. And it's for those reasons that the anode in a battery carries that negative terminus, and the cathode carries the positive terminus. The positive and negative sides of a battery, if you think about what a AA battery looks like or what a C cell battery looks like, it's always the same. There's a positive side and a negative side. And that is a key into what the materials are in those areas. Now, the problem that we run into with electrochemistry is that it can very quickly happen that these cells become polarized. Because if you think about it, if all of the electronic motion is all heading in one direction, what we would get in this particular case is a copper cell that is so full of negative charge and a zinc cell that is so full of positive charge that they would basically lock up and no more would be able to travel just from a sheer numbers kind of perspective. It would actually take a whole lot less time to lock up than you think. And that's where the salt bridge comes in. Now, the description here says that the salt bridge connects the two solutions. What that salt bridge contains is usually a series of neutral ions. So things like sodium nitrate or potassium nitrate, something along those lines. Ions that are very unlikely to react in either direction. They're unlikely to become oxidized. They're unlikely to become reduced. They're unlikely to create precipitates inside of the cells that they're being put into. And what happens in this salt bridge is the salt bridge is going to act in such a way to try to balance the charges that are coming in. So all the electrons are going into the cathode. Well, from the salt bridge is going to contribute some positive ions into the copper solution so that it doesn't get too negative in there. And on the anode side, where the zinc is getting more and more positive by the second, the salt bridge is going to give us negative ions so that that zinc side doesn't get so positive. We're going to maintain a charge integrity inside of each of those cells so that it doesn't become too one-sided in there. And that's going to allow the electrons to continue to flow in the one direction because those electrons are being replaced by negative ions from the salt bridge. So the net overall charge inside of that zinc cell doesn't change appreciably. And the same thing in the copper cell. The net overall change in charge doesn't change appreciably in the copper cell, even though we've got a whole bunch of electrons flowing into it. Positive ions are coming in through the salt bridge to balance out all of those extra electrons. But in each individual cell, you're going to see the oxidation taking place in the case of the anode, where we can actually see that the zinc is actually losing metal atoms off of the electrode itself, and those atoms are going into the solution. And on the copper side, we're going to see copper ions getting deposited on that copper cathode as the copper ions in solution get turned into copper metal. And so it's not simply enough to just connect the two wires to each other, the two electrodes to each other. The solutions that they are in are equally important, because it is the solutions that are going to stabilize and allow those electrons to be transferred in each cell individually. Now we can show this picture of a battery involving copper and zinc using something called line notation or a cell diagram. And what a cell diagram does is it shows us the whole picture of what is happening inside of that reaction. And what we'll want to do, what we will be doing is we're basically going to be showing the trip that the electrons undergo. So in a cell diagram, we're going to have a salt bridge in the middle. That's what this double line is going to indicate. On this side of the salt bridge, we're going to have our anode information. On this side of the salt bridge, we're going to have our cathode information. And so we can see that because we are drawing it this way always, we are telling the story. The electrons are going from the left side of this diagram to the right side of this diagram. And so the description here tells you kind of how to build that diagram kind of from outside in. Just understand that in the big picture, this is what you're looking at. And so we always will start with the electrodes themselves, the composition of the electrodes. So in this case, we would have zinc as the electrode for the zinc cell, and copper is the electrode for the copper cell. We can depict the cell, or excuse me, the electrode with a single vertical line. So if I were drawing this out myself, kind of telling the story, what I would be doing is I'd be saying, okay, we're starting with a zinc electrode as the anode, and it is in a solution of zinc ions. And since this is a standard cell, it would be 1 molar. So there's my anode. And then on the other side, I would have a copper electrode that has copper 2 ion in a 1 molar solution. So this is my cathode. So that's how I kind of build line diagrams, is I kind of go from left to right, looking at, okay, this is the composition of the anode. Here's the salt bridge that divides them. Here's the composition of the cathode. You can also do it the way that the book is describing, where you just build it from outside in. You start with the 2 electrodes. You put a single line to divide the electrodes from the solutions. You describe the solutions. And then there's the double line for the salt bridge between the 2. Either way works. It's really just a matter of preference there. But in the end, it's all got to tell the same story. The electrons are going from the left side of the diagram to the right side of the diagram. They're going from the anode to the cathode. We can measure the voltage associated with a cell, so half of a battery, based on something called the standard hydrogen electrode. And we'll talk about that in a second. But what it does is it is going to give us a value for the reduction potential of that cell. So in the case of the battery that we looked at, the copper cathode, copper metal in copper 2 ion solution, the standard reduction potential of that reaction, the copper 2 turning into copper metal, is positive 0.342 volts. So that reduction is a favorable process. When that reduction occurs, we get 0.342 volts out of the battery. And so what this allows us to do I'm going to come back to standard cell potential in a second. We measured all of this relative to a standard. The standard that we use is something called the standard hydrogen electrode, SHE. The standard hydrogen electrode is our 0 point on the scale. And so what we do is we hook up these other cells to the standard hydrogen electrode and see where the electrons go. Do they go into the other cell, which would indicate that it's getting reduced, and therefore it would have a positive reduction potential? Or do they flow from the other cell into the hydrogen, which would indicate that the hydrogen is getting reduced and the other thing's getting oxidized, which would give us a negative reduction potential since the stuff doesn't want to get reduced, it gets oxidized instead. So the standard hydrogen electrode is this reaction. We've got a 1 molar solution of acid and a 1 atmosphere environment of hydrogen around it. Now, the question you might be asking yourself is this, okay, I've got hydrogen, it's a gas. I've got a solution, it's a solution. What's my conduit? What's delivering the electricity? And that's a great question because neither of those things are metallic. So what's the electrode that I'm going to use actually look like? Well, we have to be careful about the selection here, right? We don't want to pick a metal that is going to be reactive with acid. We don't want to pick a metal that is going to have potential issues with it in terms of reacting with hydrogen or anything else. We've got to choose something that is inert. And the most common choice for that is platinum. So when we look at the standard hydrogen electrode here, what we will see is that it is using platinum as that conduit, as that wire that is allowing the electrons to flow in or out. Since obviously we can't use hydrogen itself. And so in terms of cell notation or diagrams are concerned, we would see that because we have no electrode of the material, we would list platinum as that electrode. And then inside of that bar, we would list out the 2 different phases of hydrogen that were present and how they are present. So again, if we're dealing with standard conditions, we're talking about a 1 bar pressure, 1 molar solution, and that's how it would look for the standard hydrogen electrode. So if it is acting as the anode, this is what that half of the cell diagram would look like. If it's acting as a cathode, this is what that half of the cell diagram would look like. Now, it might seem arbitrary, but the order here is important. Because remember, we're talking about the flow of the electrons. So if we're acting as an anode, we need to be getting more positive. The electrons need to be leaving the hydrogen. So that would mean that we're going from the hydrogen element to hydrogen ions. That's why they are written in that order. Because we can see the electrons are going from 0 state to +1 state there. And on this side, why are they reversed? Same reason. The electrons are going in, so we need to show that the hydrogen is gaining electrons. It's going from the +1 ion to the 0 element. So this order assignment here is not an arbitrary value. It is indeed a real value, and it has a measure of importance to it. So now we can look at that standard hydrogen or electrode and we say, okay, there's our standard, there's our 0 point. We can measure every other cell relative to that one. Well, what that gives us is that gives us a table of values that would indicate the standard reduction potential of every cell possible relative to that of hydrogen. And that's what these tables are all about. So in your lecture packet, you've got maybe 20, 25 pages of reduction potentials listed out in order by element. And there's lots of them here. Now, what this can allow us to do is a couple of things. First of all, it can give us an idea of overall ability to oxidize. So the bigger the reduction potential is, the more likely that reaction is going to be as a reduction. And so if I can pair them with each other, I can look at, okay, this reaction between aluminum ion and aluminum is giving negative 1.682 volts if we try to reduce aluminum metal. Well, obviously, we're not going to want to have that happen unless, let's say we pair it with actinium. Well, actinium will lose 2.2 volts if it gets reduced. Well, I can see from this, aluminum is way more likely to be reduced than actinium is. So I can use them as a comparison to each other. And what that brings us to is this idea of cell potential. If I pair together two of these reactions with each other, one of them is going to have to act as the cathode, the other is going to have to act as the anode, and unless their voltage potentials are exactly the same, we're going to get some measure of voltage between them. And we can calculate that voltage by taking the reduction potential of the cathode and subtracting from it the reduction potential of the anode. That will give us the cell potential. Cell potential, also referred to sometimes as the electromotive force or EMF, or simply just as the cell voltage. And so if we look at it from this perspective, here I have the two voltages hooked up to the standard hydrogen electrode. And I can see that, okay, copper has a value of 0.342 volts. Zinc, on the other hand, zinc was oxidized. So as an oxidizing potential, it's 0.762. As a reduction potential, it's actually the opposite. And so if I were to put the zinc and the copper together, copper, since it has the more positive reduction potential, would be the cathode. Zinc, with its more negative reduction potential, would be the anode. And 0.342 minus negative 0.762 would give us a total voltage for that battery at 1.104 volts. So the battery we were looking at the start, that copper zinc battery, generates a little more than 1.1 volts at standard conditions, which isn't half bad. So this is the table out of your textbook. It's table 17.1. It gives us a list of some of the reduction potentials based on their half reactions. And what we can see off of the list here primarily is the substances, the half reactions that are high on the list are also very strong oxidizing agents. And so on this list, we would have things like fluorine gas. Fluorine is a very good oxidizing agent because fluorine really wants that electron as part of its electronegativity. We have things like permanganate ion. Permanganate ion is a very good oxidizing agent because we've got that manganese in the positive 7 state. You've got things like chlorine and ozone here. Or I'm sorry, that's oxygen. So you've got lots of different kinds of substances here in play. In the middle, you've got the standard hydrogen electrode at 0 volts. And what we start to see after this is we start to see the rise of poor oxidizing agents, but good reducing agents on the flip side. So there is an inverse relationship that exists between oxidation and reduction. If we've got good oxidizing agents, we have poor reducing agents on the other side. So fluorine's a great oxidizing agent. Fluoride is a lousy reducing agent. So kind of similar to what we saw in conjugate theory. Strong acid, weak conjugate base. Strong base, weak conjugate acid. It's the same kind of idea. The only difference is, again, we need to look at the other side of the equation. So when I look at how lousy zinc is as an oxidizing agent, zinc ion, I have to understand that zinc ion is not going to be a good reducing agent, but the zinc metal will be. Zinc metal will give us that 0.76 volts when it comes together. And so, like I said, when we put those two together, that's where we can get 1.104 volts in total as the as that standard cell potential. Now, one other consequence of the standard hydrogen electrode and giving us all of these values is that we can actually shortcut some of our redox balancing if we have access to a table of values, because the table of values gives us the reduction half reaction in its full form. So if we know what it is that we're looking for, we can use that to kind of find it. We can do the same thing for the other half reaction as well. We just got to remember to flip the oxidation reaction around and do the multiplying with the electrons to make sure that everything cancels out. So if we know what we're doing and if we know what we're looking for, the table of values here can actually do a lot for us in terms of figuring out what it is that we're supposed to do and what that balanced equation looks like ultimately. Now, just a couple of more notes regarding reduction potentials and what's on those tables. We've mentioned this already. It's important to reiterate. When we have positive values of reduction potential, that indicates that we've got a substance that is more likely to be reduced than oxidized. The substances that are the best oxidizing agents are going to have large positive reduction potentials. On the flip side, if I've got a negative reduction potential, it is very unlikely that that substance is going to be reduced. It's far more likely that that reaction is going to flip around and turn into an oxidation potential, because the oxidation is favorable. So the more negative a reduction potential is, the better it's going to be in terms of being a reducing agent. The more likely it will be to be oxidized rather than reduced. The other important thing, and this flies in the face of pretty much everything we've done into this course up until this point. Everything we've dealt with has been an extensive property. Increase the amount, it increases the delta H. Increase the amount, it changes our value of K. Increase the amount, it changes our rate, well, not our rate constant, our rate of reaction. Everything's been extensive so far. The more we add, the more results we get. Electrochemistry doesn't fly like that. Reduction potential, E cell, that's an intensive property. So when I go to add these reduction equations together to get the net reaction, it doesn't matter that I had to multiply the anode by 3 or multiply the cathode by 2. The resulting E cell is going to be exactly the same. So I don't need to multiply the reduction potential by 3 or multiply the reduction potential by 2 or whatever. What you see in this table is what you get. Doesn't matter what I multiply these coefficients by. The number here in the end is going to be the same regardless. Important difference and distinction. Because again, we've been in this class for 20 days. That's the equivalent of 12-ish weeks of class. Everything we've done so far has been the exact opposite. Oh, you multiply the equation by 2? You better multiply that delta H by 2. You better square the coefficient. Not so here. So when it comes to calculating cell potential, there are 2 ways that we can go about doing it. If we are just looking at the reduction potentials, and we can identify the cathode and the anode, then we do just that. We just take the E cell at the cathode, subtract the E cell from the anode, and we go on with it. Now, there might be certain occasions where it is advantageous to do the second kind of reaction, the second kind of equation. And really what I'm thinking about here is if you can conceptualize Hess's law and that makes sense to you, where we've got this idea, we've got this half reaction, we've got this other half reaction, and we flip around the one reaction. So we flip around the sign of E and we add it all together. That's basically what this second equation is saying. if my approach to electrochemistry is similar to what we were doing with other reaction equations when we add them up, then that second equation is for you. Because all you do is you take that half reaction and you flip it around because it's oxidation, and you flip the sign because if you flip the equation, you should flip the sign, and you add the two together, that gives you the E cell. So really it comes down to what makes sense for you, what works for you. The net interpretation is the same. Spontaneity of the cell is linked to positive E cell values. When our E cell value is positive, that means we've got a spontaneous reaction. When our E cell value is negative, that means that we've got a non-spontaneous process. And it also means the electrons are going to still move. They're just going to move in the opposite direction that we said. So let's take our lab this afternoon, for example. You make the cells, you hook up the electrodes, you do everything you're supposed to, and the voltage you read is negative. What does that tell you ultimately? It tells you that you got your leads crossed. The thing you identified as the cathode, just maybe by pure guessing, was actually the anode. You just got to switch the alligator clips and rewrite, okay, this is actually the cathode, this is actually the anode. Because the reaction is going to run either way. Spontaneous processes happen. They happen without our outside interference. So just because we want it to happen the other way, doesn't mean it's going to happen the other way. And unlike some of the reactions that we saw in thermodynamics, where we just go, oh, that reaction won't occur. These ones will, because we're basically setting it up almost like an equilibrium. We're not just setting up, oh, I've got just these reactants, and I'm going to try to put them together to make products. In those cells, you've got the reactant and the product in the same cell, and you're hooking them together. So everything is there on both sides of the equation. So if you hook them up together, a reaction is going to occur. It's just a matter of, is it the one that you were looking for, or is it the opposite? And your measured voltage will tell you. It's positive, you've got it hooked up the way that it's supposed to be. If it's negative, you've got it hooked up backwards. But there will always be a spontaneous process occurring inside of an electrochemical cell, because you've got all the ingredients there. You're not holding back anything. All right, let's do some calculations. Let's do some practice here. We need to determine the E cell for the following reactions. So we can approach this a couple of different ways. We can look at this from an oxidation number standpoint. I've got zeros for the hydrogen and the fluorine, +1 for the hydrogen ion, -1 for the fluoride ion. So I can see that fluorine is reduced and hydrogen is oxidized. And so if E cell is equal to E cathode minus E anode, that would be E of fluorine minus E of hydrogen. I can find those values. Fluorine is 2.872 volts. And hydrogen is 0 volts. So E cell would be 2.872 volts. There we go. That's one approach that you can do. Now, if you're looking at me right now and saying, whoa, hold on a second. Where did all that come from? I don't like oxidation numbers. Get me out of here. Let me do something a little bit more straightforward for me. Remember, we do have that other approach. And the other approach would mean, okay, well, let's look at, is there a half reaction in our table that looks kind of like this? It's got hydrogen in it. I can look and, okay, the half reaction looks like this. It's 2H plus and 2 electrons make hydrogen. Okay, that's kind of the same as this one, only in reverse. So, well, in this case, I don't have to do anything. 0 is neither negative nor positive, so I don't really need to flip the sign. Okay, I've got that. I had to look for it, but it's there. And for fluorine, well, let's see, is there any reaction that looks kind of like this, where fluorine is turning into fluoride? Oh, yeah, right here. Fluorine plus 2 electrons makes fluoride. The E for that is 2.872 volts. Well, if I put those together, Hess's law style, I would get hydrogen plus fluorine plus 2 electrons makes 2 hydrogen ions, 2 electrons, and 2 fluoride ions. If I take out the electrons, that's the reaction I'm looking for. I just need to add together these two values. It's 2.872 volts. Both approaches get me to the same place. They get me to the answer that is correct, that I am looking for. They handle it in different ways. So it's more a matter of, if you are good at recognizing oxidation and reduction just by kind of looking at it, that first approach with the cathode minus the anode, yeah, that makes perfect sense to you. Okay, I just do whatever's reduced, subtract from it whatever's oxidized, I'm done. But if that doesn't work for you, there are ways that you can kind of meander your way to it using a similar approach to Hess's law. The only difference is that instead of a table of values of delta H's, you're using a table of half reactions and you're just kind of matching. So let's take a look at this second one. Here I've got nickel turning into nickel 2+. So there'd be a pair of electrons there as well. If I look at my reduction potentials, the opposite process for nickel would be negative 0.251. So reduction potential would be negative 0.251 volts. I also have cerium 4 turning into cerium 3. And I can find that here, cerium 4 to 3, 1.72 volts. So with the two reduction potentials, if I didn't want to mess around with flipping the sign or anything like that, I could just simply go that E cell is equal to 1.720 volts minus negative 0.251 volts. 1.72 minus negative 0.251 would give me 1.971 volts. The other approach would be, I could recognize, hey, that nickel reaction, that's not a reduction, that's an oxidation. So if I want to turn this reduction potential into an oxidation potential, I just need to flip the sign, 0.251 volts, and now add together 1.72 and 0.251. I'll get the same 1.971 volts. It's the same thing either way. It really just comes down to preference and what you're comfortable with. And believe me, once you do some of these, it's not too terribly difficult to kind of just get into a groove, get into a pattern, find something that works for you. All right, let's do another one here. The standard reduction potentials for the half reactions in single-use alkaline batteries are these. You've got zinc oxide turning into zinc. The reduction potential there is negative 1.249 volts. You've got manganese dioxide turning into manganese 3 oxide and 2 hydroxides. The reduction potential for that is 0.15 volts. What is the net ionic equation? What is the value of E cell? Okay, so when you're presented with a problem like this, you've been given 2 reduction potentials. The approach here is we need to figure out which one is actually going to get reduced. So which one is going to stay a reduction potential and which one is going to eventually get oxidized? Which one's going to flip around? And the way to identify it is actually easy. We just look for the one that has the better the better reduction potential, the more positive value. More positive value is this one here. So we're going to have 2 manganese 4 oxides and water and electrons turning into manganese 3 oxide and 2 hydroxides. And the E value here is going to be 0.15 volts. Going to have to flip around the other equation because something has to get oxidized. So we're looking at zinc and 2 hydroxides turning into zinc oxide and water and 2 electrons. And the E value for this, I am going to flip this around, 1.249 positive. This is one of those circumstances where adding them together definitely makes the more sense because I've got to figure out what the balanced equation is in the process anyway. Why not do the same thing? Add them together, add together the E cells, treat this like it's a Hess's law problem. When I do that, the hydroxides cancel out, the waters cancel out, the electrons cancel out. So all that is left is I've got 2 manganese 4 oxides and zinc turning into manganese 3 oxide and zinc oxide. And the reduction potential for this 0.15 plus 1.249, just adding them together, Hess's law style, would give us 1.399 volts. So you can see this is why this is called a dry cell battery, because if you look at the reaction itself, there's nothing in this reaction that is aqueous or liquid. You've got basically solid pastes reacting together. And so long as you've got some means for those solid pastes to interact in some kind of efficient way, you'll get electricity flowing through. All right, any questions with this? All right, so we're going to close today by having you do a couple of examples yourself here. So let's start with this one. What is the value of E cell for the reaction between chlorine and iodide to make chloride ions and iodine, elemental iodine? So you're going to need your reduction potential tables either from your textbook or in the appendix tables that are posted online. So go ahead and grab those if you can and come back and we'll talk about this in a few minutes. All right, let's see how we did. So the reaction that we're looking at is this one. And if we break it down into pieces, then what we end up with are these 2 half reactions here. The reduction of chlorine to chloride gives a reduction potential of positive 1.362 volts. The reduction of iodine to iodide would give 0.5355 volts. Now, here's what we have to recognize. We can't just simply add these 2 together. We add them together, we get chlorine plus iodine plus 4 electrons makes chloride and iodide. That's not the reaction we're looking for. It doesn't match up. So what we have to recognize is one of 2 things. We either have to recognize that the iodine, its reaction is flipped around, which means that this is the anode and this the cathode, or we have to recognize that this reaction for iodide is the opposite and we need to flip around the equation. And turn that reduction potential into an oxidation potential. One of the 2 has to happen. I either have to assign a cathode and an anode to them based upon the reaction that I'm given, not necessarily the values themselves. Or I have to flip it around to get it to match. Either way, I'm getting an E cell value that is 1.362 volts minus or plus a negative 5355 volts. Which to 3 decimal places would be positive 0.827 volts. So either way you cut it, whether you flip the reaction and flip the sign, add them together, or you recognize cathode and anode and you do your subtraction, 0.827 volts is going to be your answer. And so that's probably the hardest thing to put your brain around as far as this electrochemistry stuff is concerned, is I'm given a table of just reductions. How do I figure out how to manipulate it to get the equation that I'm actually seeking? And as has been the case throughout thermodynamics, there are multiple ways to do it. You just have to find the one that is the most comfortable for you. And the only way to get to that level of comfort is through practice. That's what the homework assignments are for. All right, any questions about this example? All right, we'll do one more and then we'll put to end lecture for the day. Slightly more complicated one here. We've got the reaction between nitrate ion and copper metal to make nitrogen monoxide and copper 2 ion. And there's some hydrogens and waters in the way as well. But when you're looking at your tables of half reactions, that's what you want to focus on. You're going to want to focus on, is there a reaction in acid between nitrate ion and nitrogen monoxide? Is there a reaction between copper and copper 2 ion? Those are the half reactions that you need to look for. So same thing, take a few minutes, try to work your way through this. We'll come back and look at it in just a bit. All right, let's see how we did. So again, the typo here might have thrown you off a little bit. Just because if you're looking for something that had 2 nitrates on the one side and only 1 nitrogen monoxide on the other, that might have thrown you for a little bit of a loop. But what it really came down to is, if we can move on here, we had to identify the 2 half reactions. And what we also had to kind of remember and strip out of this was the coefficients may not have matched up perfectly. Remember this, that was a complete balanced equation that they gave us. So that's after all the multiplying and recombining takes place. So when you're looking at these tables of values, what you really want to kind of pinpoint and look at is the structure roughly the same? So not am I looking for 3 copper turning into 3 copper 2s, but rather, is there a reaction that turns copper 2 plus into copper or vice versa? And there is, and the reduction potential for it is 0.344 volts. We need to do the same kind of thing for the nitrate. We're looking for the conversion between nitrate and nitrogen monoxide. And we know that there's going to be hydrogen ion on the one side with the nitrate and water on the side with the nitrogen monoxide. And so if you do a little bit of digging on that nitrogen table, about midway into the table, you'll find this half reaction. And the reduction potential for it is 0.957 volts. So right away, you should be able to look at this and say, okay, it doesn't match in value, but it does match in kind with the equation. So this must be our cathode, which means that this would be our anode. And if we take it from there, we would get 0.957 volts minus 0.344 volts. And it would come out to 0.613 volts. So 0.613 volts is the reduction, or is the, the cell potential for this particular battery. Now, if you got kind of wrapped up in all of the coefficients and you said to yourself, okay, I get that this is happening, and I know I need to flip this top equation around. So it's really copper turning into copper 2+ and 2 electrons, and the cell potential is actually the opposite of this, and the other one stays the same. If you got caught up in the coefficients and trying to make all of it match and go, okay, well, this needs a triple and this needs a double to get it to match up, the easy mistake to make in this Hess's law approach especially is to treat it all the way like it's Hess's law. It's not. We're using a similar approach, but in execution, we have to remember that these E values are intensive. So I don't go, oh, well, you know what? I multiplied that by 3, so I got to multiply this one by 3. I got to do that one by 2, add them together to get my final voltage. I can't do that. I can't do that. That's going to lead me down the wrong path. You can do the coefficient part. You can get yourself to the top equation that we're interested in, but you can't touch those E cell values other than to flip the first one from positive to negative when you add them together. The end result, you still get 0.613 volts. So that's kind of the danger with the flip it around and add them together technique, is if you get too much into your own head that this is Hess's law, just done up a little bit different, you're going to run into that problem. And we don't want to run into that problem. So just kind of got to remember, separate that aspect of it. Yes, you're going to need to multiply those half reactions by coefficients to get them to line up, to get them to match up. But the E values are sacred. They don't get touched other than to change the sign if we flip them around. All right, any questions? All right, last thing to do. We've completed our first day of study of electrochemistry. Tomorrow we'll get into kind of the other aspects of electrochemistry, tying it more definitively to spontaneity, tying it more definitively to delta G values, to equilibrium constant values, and also looking at non-standard conditions and how that can kind of play a role as well. So that's kind of what's on the horizon, but celebrate. We're done with this stuff for the day.